Module 2.3, Implementing Density Functional Theory in Practice. In this module, we will learn about practical aspects of implementing DFT calculations, what kind of inputs and outputs that are going to be while learning a DFT calculations, importance of approximations such as the choice of basis sets, pseudopotentials, convergence criterions, understanding the meanings of different parameters that are important for running DFT calculations and so on. Some of the practical computational software that are available out there, some of them are commercial, some of them are open access, so we'll learn about that as well. So before running any software or multi-scale modeling software, it is important to understand what is my input and what is the output of these calculations. So for atomistic simulation, such as density functional theory calculation, we need atomic structure information. And when we say atomic structure information, what it means is atomic positions and lattice parameters. So atomic positions are 3D coordinates in space, so x, y, and z coordinates of each atoms. And lattice parameters, especially for solids such as aluminum, silicon, gallium arsenide, nickel aluminum alloy, so on, are repeat units after which they can be repeated infinitely. So that's important to know. So where do you get this information? You can get the atomic positions and lattice parameter information from experiments such as X-ray diffraction, nuclear magnetic resonance measurements, or we can also get it from openly available databases such as crystallography open databases, Jarvis DFT, Materials Project, OQMD, and so on. When we say initial atomic structure, now this can be different forms. It could be primitive cell, so the smallest unit cell required to represent a material, or it can be conventional cell. It can be perfect cell, or it can be defect and interface cell. So while going through this exercise, we will try to point out what's the difference between them. So for example, aluminum on your left-hand side, you can see it is conventional cell. And usually in conventional cell, you have 4 atoms in aluminum conventional cell, and there only one atom in the primitive cell. Now, we want to solve Kohn-Sham equation, but in order to solve this, we need to expand the wave function here, for example, psi, in a possible combination of basis set. So C alpha, phi alpha, and their combination. So basis sets basically simplify the problem of solving Kohn-Sham equation by expanding the wave function in a manageable set of basis functions. There are different types of basis functions. It could be localized orbitals, such as the Gaussian or Slater type orbitals. These are especially very important for molecular or isolated systems. Or there could be plane waves, such as for solids such as aluminum and so on, which are periodic usually in theory. And this any periodic material can be represented by their lattice vector. So A1, A2, A3. So you can see here on your left-hand side, a system is assumed to be placed inside a unit cell defined by the unit vectors A1, A2, A3. And the volume is usually there given by this equation on the left. The A1, A2, A3 also represent the X, Y, Z repeat units. Now, in order to represent these plane wave bases, which are going to be the importance for our course here or in this module, we will have to convert this into a reciprocal lattice vectors given on by the right hand side equation. And based on this B1, B2, B3, where it is connected to the A2, A3, A3, A1, A1, A2 lattice vectors, pi factor and the volume omega, we can get this wave vector to satisfy the periodic lattice, which is given by G, I1, I2, I3, which is again the X, Y, Z direction. And this is how we establish a relationship between a basis set for periodic materials such as aluminum. Now, another assumption that is important for solving a Kohn-Sham equation is pseudopotential. So pseudopotential are effective potential used to replace all electron potential near the nucleus. And It is very useful for reducing computational complexity by focusing on valence electrons only and effectively ignoring the core electrons, because valence electrons are the ones which participate in a chemical reaction or in a deformation phenomenon and so on. So there are different types of pseudopotential: non-conserving, ultra soft, and pseudopotent and the PAW, a projected augmented wave. So I'll not go in detail of this, but basically in PAW, for example, projected augmented wave, it is a method to provide the accuracy of all electron with efficiency of pseudopotential. And you can see, instead of having all electron wave function, which is given by the wiggles here, we are trying to represent the core by a smooth function, and then the valence electron is by another smooth function. In that way, we try to lessen the computational complexity and make it numerically stable. Now, how do we combine this idea of basis set and pseudopotentials? It is important to match the choice of basis set and pseudopotential based on the problem you're trying to solve. So especially for solids, we are using PAW basis set and not localized basis set. And when we use basis set and pseudopotential, there are certain things to consider. So a basis set, for example, plane wave basis set, needs to be converged, and their key points, the key point mesh needs to be converged. We have to check the pseudopotential accuracy and to check also how transferred they are across different chemical environments. So there are different softwares for running density functional theory calculations. Some of them are VASP, Quantum Espresso, GPaw, Abinit. So VASP is a commercial software, others are not. So in this tutorial, which is the next module, we'll be using GPaw softwares. They all solve this Korn-Sham equation, but they have different types of input-output files. And we'll be looking at least one of them. And before running any software, it is recommended that we read the documentation as much as possible. So we learned about the inputs, which is the atomic structure information, the basis set, the pseudopotential, all types of conversions that we have to do. And then the output is electronic density of states, charge density, optimized lattice constant. So we give the initial lattice constant. After the relaxation, we can get optimized lattice constants. Stress strain curve, which are especially important for mechanical engineering applications, and other properties such as bulk modulus, elastic modulus, thermal conductivity, and maybe less important mechanical properties such as electronic band gap, magnetic moment, and many other properties. So on the right-hand side, I show you some of the example properties that we are going to calculate or predict, and we will actually run that in the next module. So look forward to that.